So I'm going to discuss two things really. So one is kind of the push we have currently at FAIR to build a world model through JEPA architecture. And another project, which is more like a general SSL, which is how we can scale Dino and show that you can match clip level performance on a V2A task. Okay. So I don't think I can do as good a job as Jan as motivating the example, but I'm still going to show this video because I think it's funny. So what you're going to show is a raven that needs to solve a problem. So it's going to have to reach some food in some kind of tube, but you cannot reach it directly. So you have to find a solution here. So yeah. So here's a raven. Here you see there is some kind of tube with some water, and there is a food inside it. And so you can see he's kind of picking a small rock, putting that into the water, and eventually he will make it. It's kind of picking the food. So I think it's a kind of a very nice example because it shows that many species have the ability to solve problems that require planning. You need to infer a set of action to reach a goal that require common sense understanding. You need to understand that if you put a rock into the water, the level will go up. And also, of course, like low-level motor control. And really the kind of whole motivation behind this kind of line of work with JEPA is how do we add those ability into our machine. Okay. So, nothing new here, but how do we enable planning in machine? So one of the common building blocks that's often come in the literature is the idea of world model, or it's also called like mental model in cognitive theory. So, oh, got it. So basically, it's kind of also, yeah, I mean, we heard the term world model a lot these days, so I'm going to try to define it. And, I think in essence, a world model is something that is able to predict something it doesn't see directly from the input. So for instance, here you see the beginning of a video. You might condition your world model with an action, and you try to predict, what's going to happen if you apply this action. And of course, once you have a world model which is trained, you can use it to plan and find a set of actions that allow you to reach a goal, right? And so the big question now is how can we learn a world model? And so, yeah, I'm not going to repeat everything, but basically, the way to world model, we believe, is to use SSL. And the main argument for that is, the world is not fully predictable. Like it's kind of a waste of compute to try to predict every pixel in your video. And so you need to abstract your prediction. You need to predict in a compressed or abstract representation space. And this is kind of the whole idea behind JEPA, as Jan was mentioning. And it's also something that worked pretty well and demonstrating a huge amount of success in vision. Like if you want to have like good vision representation, the main way to go is to use like Dino type model, which also work with similar principle. Okay, so we kind of started this effort like almost 2 years ago, I would say. And so the first question, so we had some work with JEPA and images that was working pretty well. And now the first question we ask ourselves is, can we extend those principles to learn from video? And this is this paper revisiting feature prediction for learning visual representation from video, which was led by Adrien Bard from Paris, and with a bunch of amazing co-authors. And yeah, you might recognize the picture, but so really at the core of the approach is the idea of learning by predicting missing information, but in a learned representation space. So you have an input, so it's kind of a video. You're going to apply some kind of corruption. So here we use masking. I have to say it's very sensitive to the type of masking you are using. So we are using tube masking where we mask everything temporarily. You get your corrupted input. Then you're going to pass your corrupted input into an encoder. So in this work, we use like a vision transformer most of the time. You get a representation. You're going to feed your representation to a predictor, but you're also going to feed extra information to the predictor. So here we're going to feed the localization that we are trying to predict. So you not just try to match the two representation, you try to predict what would be the representation as a specific localization of the videos that you don't see. Then you're also going to encode the target. So the target is a clean video that you're going to pass through the encoder. And then you can compute like a divergence loss. So in this work, we use the L1. So the main difficulty with this type of architecture is how to prevent collapse and how to define the prediction task. So to prevent collapse, we use a distribution-based mechanism. And I would say it's kind of mostly a technical depth, in a sense that when you use vision transformer architecture, it's kind of very like combining vision transformer with a distribution-based approach work very well. It has been used in DynoV2, for instance, that also use vision transformer in JEPA. But the issue is with this type of approach, you introduce a stop gradient, right? So basically, you have your context encoder, and your target encoder is going to be an exponential moving average of your context, and you're not going to backpropagate through the target. What it means now, once you have a stop gradient, is you don't have access to the loss you optimize anymore. You just have access to a proxy metric. So through pre-training, you cannot really understand that if your model is, I mean, you don't have a well-formed SSL loss. The only thing you can do is look at downstream task to see if your model is working or not. So it does have a bit of complexity empirically. Okay, so we have a recipe to try on video. Are we going to validate our approach? So, you know, at this point, we are kind of focusing really on the representation learning part. So really like self-supervised type evaluation. So what we do is we take our model, we're going to froze our encoders, and then we're going to fit a bunch of probes that are going to decode the representation into a set of actions. So it might be like image classification, action classification, or even like some kind of spatial temporal action detection. In practice, we use like small attentive probe to kind of back the representation into an interpretable space. So yeah, I don't want to have some. So I'm just going to show a few results, not everything, but just to give an understanding of what are the model capability. So I'm going to focus on two tasks. One, which is kinetics. It's kind of an action recognition task. But as you can see with this example, this task is very much appearance bias. So with just one frame, you can have an idea of what's going on in the video. The other one is something, which is a data set that have been created to be adversarial with respect to appearance. So you actually need to have an understanding of motion and a bit of memory to be able to classify the action. And so what we see with JEPA is that we have a model which is very good on motion-based tasks. So we are kind of state-of-the-art, or we were state-of-the-art at the time of the chef on the something task. So if you want to have features that have good motion understanding, it's a pretty good model. And on appearance task, it was reasonable, but not as competitive as let's say DynoV2. And we now know that it's mostly a function of your pre-training data distribution. We train on video. Video has limited visual coverage, so you don't see as much diversity in terms of visual object. Another interesting property of JEPA is it works very well in a low-shot regime. So here we have a plot where the x-axis is a number of examples per class, and the y-axis is something v2 performance. And this is a number of examples we use to kind of learn the attentive probe on top of the representation. And so we can see that even with 50 examples, we get reasonable accuracy and much better accuracy than a pixel level prediction test. So it kind of shows that when you predict in a learn representation space, you're able to kind of abstract and have more structure into your space because you can adapt your representation more easily. Few more ablation. So yeah, I was discussing before like the sensitivity to the masking task, and it's actually something we spend a lot of time for this project, and this is what this table is showing. So here we try different type of masking. One is kind of random tube, so we just have a small tube that we randomly mask in a video. One is kind of the multi-block strategy, so we basically sample blocks, so big tubes spatially, and we kind of mask it through the video. So yeah, the difference between causal and non-causal is at some point we're going to mask the full video. And the last one is the multi-block. Is just, yeah, we have those big blocks that we mask through the full video, but we don't mask the end of the video. Yeah, that might be a bit confusing, but the point of this plot is to show that what you need to make this type of approach work is to break the spatial and temporal correlation. So, a video, you have a lot of temporal correlation. So if you don't do tube masking, but just mask some pixel within the video, it's not going to be a hard enough prediction task. same thing spatially. If you don't mask neighboring patch, it's going to be too easy a task. And so you're not going to learn interesting representation. The other table just compares the pixel level prediction versus feature level prediction. So either you have a VJEPA, I mean, it's not a VJEPA, but the same type of architecture, but now the loss is in pixel space, or you use a target encoder to kind of compute the target. And so, yeah, just to kind of validate the point that indeed you learn a better representation when you predict in pixel space. Okay. So can we leverage JEPA style architecture to learn from video? Yes. I mean, we can learn good representation from pre-training a JEPA on video. But of course, the method is not without limitation. One thing that I touched on already is we don't have an explicit loss function. So it kind of makes the empirical exploration around this approach a bit tricky. And when you want to scale the approach, it's possible, but it requires a bit some work. We have a sensitivity to masking, which is a bit disappointing in a sense that with SSL you want to learn a universal representation, but then you have to kind of specify uncrafted masks to make them work well on some downstream task. Last one is this is kind of a video approach. We only train on video data, and so we have limited visual coverage. So that kind of impacts the quality of the representation for appearance feature. But I think the main limitations here is like we started with this motivation of learning a world model, and we focus only on understanding tasks. So there is kind of a disconnect, and this is what we're trying to address in the next project. So the next project was led by Conta Garrido, and actually here we look at two things at the same time. How good is a JEPA architecture at predicting, not just representing, but also can it understand intuitive physics from video? So how to evaluate JEPA for prediction? JEPA is trained to predict missing information in representation space, and this is very great for downstream recognition task. However, we train that with an energy function, so we don't have an explicit likelihood on prediction. So we cannot just measure the likelihood of future prediction. And also, it's in a representation space, so we don't have an easy way to interpret the representation that we predict. So JEPA learns an energy function that can be used to rank potential feature. And actually, this is a great property for intuitive physics, and I'm going to explain why. So what is intuitive physics? So, in general, in the world, we expect objects to behave predictably. So, they don't appear out of thin air. They don't change shape arbitrarily. And this is why, magic tricks are surprising, because usually they break our expectation of the world. And intuitive physics understanding is trivial in human. But there is a lot of work showing that even like most recent models kind of struggle to understand those basic concepts, which kind of echoes the Moravec paradox. And so when we test for intuitive physics, both in children, for instance, or with model, we usually have this setup where we have two videos that are pretty similar, except for one physics breaking event. So for instance, I mean, it should be pretty obvious. So here you have a ball, then there is an occlusion. And here you see that the ball is reappearing on the other side, while in this video, the ball is going to disappear. So here there is a breaking of intuitive physics. So how do you evaluate for intuitive physics? So in cognitive science, they use what they call the violation of expectation framework, where they're going to show two videos, one which is physically plausible, one which is physically impossible. And they're going to measure some kind of metric of surprise. So for instance, for young kids, it's going to be what is the attention pattern. And based on that, they're going to see which video is the most surprising. And this is the one that's going to be physically implausible. And actually, so this is what this is showing here. And we can use a very similar protocol with a JEPA model. So basically, we're going to have the same beginning of the video. We're going to predict the future. And then we can compare the prediction with the actual future, compute an error. And the prediction with the highest error is the prediction with the highest surprise, right? So how do we compute surprise with JEPA? So we're simply going to use some kind of, because since, yeah, I have to say JEPA is trained on 4-second length video, so it doesn't have infinite context. So to apply that to a bigger video, we use simply a convolution. So we're going to slide our video encoder and predictor and compute a surprise at different time steps. Okay, so we repeat this operation. And then we're going to have a surprise metric over time. And hopefully you would see the surprise peak occurring at the same time as the physics breaking event. And when you want to compare two videos, you can simply aggregate this metric using average or some kind of max aggregation operation and use that to detect which video is the most surprising. Okay, so we have some kind of evaluation protocol. Now what are the benchmarks we're going to use? So the first one is InFlavor, which is real video, quite constrained visually. But so here you see you have some first priming event, so where we show a cup and there is a hole in the cup, right? And then you're gonna take a pen, put that in the cup, and so the model has to remember that there is a hole in the cup because it has to fall through, right? And this is quite a hard task because it both tests for intuitive physics understanding, but also memory. The other one is kind of a grasp, which is a more synthetic one. And here you have a ball rolling, and one of the velocity, let's say, is not really physically accurate, and so the model has to detect that. And the last one that I show already is InFiz, right, which was done by Emmanuel Duplou, another researcher at FAIR. And yeah, one point I want to emphasize is, even if those data look very simple for us, it's actually pretty hard for machine. As a bunch of papers that introduce the data set reported. And the nice thing about those data is really they allow to test for specific intuitive physics property. Yeah.
Can we test on some of the video generated by Sora?
Yeah, we did not have access to Sora, but other paper kind of report limited intuitive physics understanding. But I can come back to this point. Like, I think it doesn't mean that generative model cannot solve those tasks. So here's a kind of main results. So we have our three data sets: InFiz, Grasp, InFlavor. So this is the average performance across all the intuitive physics category. So in gray, you have the performance of a random network. So same architecture, we don't train the network, we just initialize it at random. Yellow is a LLM, Gemini. Green is Gwen. Blue is pixel level prediction, so it's a video MAG, so a bigger model than our JEPA. And our brown is kind of JEPA. And so what we see here in this plot is only kind of latent level prediction can have some kind of reliable understanding of intuitive physics. It's pretty good on InFiz, and then kind of decrease for the other data set, but it's already much better than random. When it's not totally clear for the other approach, especially for the VLM type of approach, if they have significant understanding of intuitive physics. Okay. Yeah.
Where is the memory coming from in this situation?
Yeah.
The fact that the cup was
Yeah, so basically, I mean, one of the limitations of the current model, so we kind of process a clip at a time, and a clip is like 3 seconds, so we have a 3-second memory. So if your priming event is before that, there is no way for the model to solve the task. Oh. And this is what we see actually here. So here we see the performance for the different category of intuitive physics understanding. So object permanence, continuity, shape consistency, and so on. And we also compute like a statistical test, as you can see. And this is only for the VJEPA model, but on the different data sets. So each color corresponds to a different data set. And so what we see is on tasks that doesn't require memory, so usually object permanence, continuity, and we know that by looking at the task, we perform pretty well. But on tasks that require like a more memory, and usually this is a task related to InFlavor. So gravity is a task where you have a hole in the cup. Here, the model is not able to solve that for now, and we believe it's because it doesn't have enough memory. Yeah.
Model comparison, are all the models trained on the same data?
No. So we train our model mostly on YouTube data, so on tutorial video, so real video, nothing related to intuitive physics. Video MA is trained on a very similar data set, not exactly the same data, but same type of distribution. And for the Gemini, we don't know what they train on, and Gwen actually don't know either. So yeah.
Right. And second question, how sensitive is this to hypermasking?
Yes. So actually, I don't have this result in the slide, but while, you know, for classification task, the type of masking is very important. Here, it doesn't matter at all. So it's more like a low-level type of task, and even random masking work pretty great. So yeah, one obvious limitation here is memory. And yeah, there is also some kind of deficiency in the task design, but yeah, I'm not going to go into the detail. Another thing we look at is the correlation between the model performance and human performance. So here on the y-axis, this is the model performance, and lower is better. On the x-axis is the human performance. And I think the interesting thing to see in this plot, and yeah, the human performance is actually provided, it's on the infis task, and this was captured by Emmanuel Dupont, and he was created the task, so he provided a caption. And so the interesting thing to see is basically the model struggle on tasks where humans struggle as well, right? So for instance, when you have occlusion, usually a model make more error and human make more error. When everything is visible, you know, both model and human perform better. Yeah, a bit to touch on your question. So we also run some ablation on scaling. So here is two plots. On the first plot, we kind of scale the dataset size. So going from 128 hour of video, everything is YouTube tutorial video, to up to 14-year of video. For those tasks, not a big effect. You know, if you have enough hour, even at 128 hour, you do reasonably well. Similar thing like for when you try to scale the model, you know, from a base to a huge or 800 million parameter model, you don't see a huge scaling trend. It does get a bit better, but it seems to see that, you know, if with this kind of a feature prediction task, it's quite easy for the model to grasp this concept. It's not something very complicated to learn. Okay, so second question, can we leverage JEPA to solve predictive tasks? Yes. So, I mean, to my knowledge, this work is the first work to show that we can solve intuitive physics with just by learning from you know, video. Previous work in this literature usually have some kind of a core knowledge hypothesis where, you know, you need some kind of uncrafted abstraction like segmentation mask object to be able to make progress on those tasks. Actually, a purely learning approach based on, you know, video data and predicting in latent representation space can also solve this task. You know, models still struggle for tasks requiring long memory. One limitation, as you can probably have seen in the example, is this set of tasks has limited visual coverage, right? And so while it allows us to kind of test for very specific property, it's not very broad in terms of general coverage. Okay. It's how much time do I have? Okay. Oh, cool. Oh, I'm good. Okay. So now, okay, we still are missing some kind of component, you know, if you want to have a full-fledged role model. And the last component is, you know, can we condition an action and kind of predict the effect of an action and start to kind of tackle planning task. And so I don't have a lot of results to share yet on that because this is kind of future work or current exploration. But I can share, you know, what is the current mindset we have and what is the set of hypotheses we want to explore in this space. So in order to plan, we need to predict the effect of action. And one of the issues you see when you go into that space is you don't have a lot of interaction data. And what I mean by interaction data is, you know, video plus action, especially because we want to focus on real world application. We don't want to go into simulator, right? So for instance, if you look at a data set like Droid, which is a Franca robotic arm in different environments, you have around like 300 hours of video. And it's actually less than that because you have like 4 views or 5 views per robot. So you have to divide this number of hours by 5. While if you take like a data set like YouTube temporal 1P, which is just data from YouTube, you get on the order of 1 million of video. But actually, this kind of data problem is a good news for SSL because, you know, the whole point of SSL is to learn a good prior of the world and have some kind of label efficient way to apply the model to downstream task. And this is a type of solution we are kind of currently exploring. So basically, we train a JEPA model, you know, with some change, but roughly similar on a large scale of observational data. So a lot of video from internet and trying to solve this kind of mass decisioning task. And then after training, we have a second stage where we adapt the model for causal prediction on robotic data. And so here, basically, we're going to have a video plus some action. And at each time step, we're going to try to predict the next time step. So it's going to be an autoregressive model specific for the droid data. So this is the type of solution we are kind of exploring. And I just want to show a result because I think it kind of communicates well where we want to go. So, I'm sorry. Okay. So here's a robot that we have in our lab in Montreal. And we don't have any training data of this specific robot in our training set. We don't train on this robot. We don't have any camera calibration. We just put a camera roughly at the same positions as the droid data set. And then we kind of deploy our world model. And so we use goal condition planning. So the first 3 frames going to be 3 goals we're going to we're going to provide to the system. So first, when it grabs the cup, then when he has the cup up, and then when the cup is done, right? And then we're going to do a closed loop MPC using cross entropy method and our world model. No training, everything is 0 shot. So first you have to go back to the original position, and you can see the model is going to start grasping the cup, putting the cup up. Now it's going to go to the last goal, and then second goal, sorry, up on the shelf, and then you drop it. So I think it's kind of a pretty exciting result. It's kind of so Cathy kind of shows that you can apply this type of MPC approach to solve a problem in simulation. And here what we see, and it's pretty early, so we have to make sure everything is robust, etc. But at least it seems plausible that we can use the same type of approach to solve real-world problem. Okay. So conclusion to the set of questions. So I think we're close to have like all the necessary tools we need to build one model with SSL and start deploying that to solve like a prehensile task with a robot and with object interaction. So I think it's actually quite an exciting area. Okay, any question on this? Otherwise, I'm going to change topic a bit.
It's a conceptual question. So in this case, you're optimizing for action.
Oh, can you use your mic?
So you're optimizing for the most like low-level actions, right? So
yeah.
I imagine in a long sequence of actions, it's going to get intractable to optimize. Is there like
so that's why we provide sub-goal for now. One limitation we have currently, and again, it's very early results, so I don't want to oversell the result, but we train on droid data, and droid video are like 2 to 4 seconds on average. So basically, our planning horizon is like 2 to 4 seconds. After that, it's a bit off. So to kind of get around this problem for now, we provide sub-goal. So we first set the robot to go to the cup, then go up, and then put it down. But I think it's mostly like you have 2 ways to deal with this problem. One is to introduce the concept of value function, to ease the planning. The other way is just to improve your predictive model, right? And spend more time, more compute and inference time to find a good solution.
Thanks.
Cool. So now I'm going to switch topic a bit and present a recent work that I think we submitted at ICCV. And actually, this work was led by Davin Fan, who is a researcher at FAIR, and it was also a joint collaboration with NYU. So Peter from NYU, Salim from NYU, and also Amir, who is in a room, contributed a lot to this work. And so really, I mean, in this work, we kind of revisit the question because it's not really a new question, but it's what is the importance of pre-training data for SSL and especially for scaling SSL. And this project kind of started, I think, with a discussion between David and Amir and this observation. So, we work on SSL. We want to learn like a good representation, like a universal representation to solve many tasks. But in practice, the dominant paradigm to solve like VQA tasks is the clip model. So at least until now. So here you have a set of blue line, which is a variation upon clip model. On the y-axis, you have a bunch of VQA tasks. So this is from the Cambrian 1 evaluation protocol. So it's a bunch of VQA tasks that are specific to general knowledge, OCR and chart, vision-centric, or general, yeah, well, I'm not sure what's the difference between general and knowledge, but probably Amir know. And here you have a set of red and green curve, which is basically methods that are trained with SSL. So it's mostly Dino-based method. And you can see that if you apply Dino on this set of VQA tasks, you're not as competitive as CLIP. And this is especially true for OCR and chart, right? So now, if you compare the two approaches, you have, I would have two main differences. One is self-supervision versus language supervision. With SSL, we only have access to the images, and we define a pretext task, data augmentation, masking that we use to learn augmentation. The other one is CLIP, use language supervision. So you have a caption associated with the image, and you have a contrastive loss to kind of match augmentation of the caption with the augmentation to the image. And so you could argue that, since you are interested in VQA tasks that require, language in essence, maybe having access to the supervision is very important in this case. But there is another difference. Like, if you look at current SSL approach, including Dino v2, most of them are still trained on ImageNet-like distribution. So for instance, Dino v2 is trained on the LVD dataset, which is 140 million images, but it's kind of built to be similar to the ImageNet-like distribution. On the other hand, all the clip-based approach are trained on, image or crawl from the internet, and at a much higher scale, right? They are usually like from 400 million to a few billion, right? And kind of raise this question, is the performance gap due to the language supervision part, or is it due to the data distribution? And we know from previous work in SSL, for instance, one of the work we did with Randall, looking at the impact of the pre-training task with respect to the data distribution, or even the Dino v2 work. A big contribution of this work was this kind of automated creation approach to kind of scale SSL. So we know that data is important. So here we kind of choose to explore the later hypothesis and say, okay, if we close the gap of data, what happened to the performance? Okay. And so this is kind of the main idea behind this work. So basically, we're going to take a SSL method. We're not going to innovate on SSL. So here we're going to use Dino v2 mostly. And instead of training on ImageNet or ImageNet-like dataset like LVD, we're going to scale that to web scale images. So specifically, we're going to use MetaClip, which is a dataset that has been introduced by Meta to reproduce clip, and that provide like billion scale diverse image from the internet. Of course, as we scale the model, there is few other knobs we can use. One important one is scaling the model size. SSL, the whole motivation of SSL is to be able to train bigger model, really to harness the power of data. And as we're going to increase the scale of data, we want to increase the scale of the model to make sure we don't underfit the distribution. And to make the comparison more relevant, we're going to focus on VQA tasks. So, we're going to take the task where clip is the best and try to see if we can match this performance with a SSL-based approach. So specifically for evaluation, we're going to use the Cambrian 1 evaluation protocol. So what this does is basically you're going to have a predefined data set for alignment. So to align your encoder to the LLM that we're going to fix across the method. And so when we're going to do this alignment phase, we're going to froze our vision model. So, okay, let's maybe take a step back so it's more clear. So first, we're going to pre-train either a clip model or a SSL model on a meta clip, right? Then we're going to froze this model, and we're going to adapt it for a multimodal large language task. So here we're going to use the Cambrian protocol. So we're going to have a connector and an LLM, like a Llama 3, and we're going to fine-tune that, just the connector and the LLM on an alignment data set. And then we have a set of tasks that we're going to use to evaluate the model. Zero shot, let's say, so we don't know if it's really zero shot with respect to the alignment distribution. Okay, so let's scale Dino v2 on MetaClip data. So we're going to use 2 billion images in this experiment. We're going to scale the model starting from the VIT1B, so the VITG that was provided in Dino v2 up to a VIT 7B. And yeah, so we introduced a specific model configuration in the paper. And yeah, we're going to use VQA for evaluation. And here's the result. So on the y-axis is the parameter, on the x-axis is the accuracy. So here's the average accuracy on all the tasks, and here's the per domain kind of accuracy. And so what we see here is like, okay, if you pre-train a Dino 1 billion parameter on MetaClip, is not competitive yet with Clip, but as you scale the model size, you actually scale better than Clip in this context. And eventually you can match and even outperform Clip in terms of average VQA performance. And so this kind of answer already the initial question and shows that, you know, maybe the confounding factor when we are comparing the model is kind of the data distribution. And you know, we need really to kind of compare things in the same setup to have more definitive conclusion. Yeah, so maybe unsurprisingly, if you train with a SSL-based approach, you excel on vision-centric VQA. So this is task where you're supposed to use more vision-related information to solve the task. But what was kind of surprising is to see that the gap on OCR and chart. So it's like, you know, you have a question with respect to a chart, and you can see as you scale your model, the gap is kind of closing quite well on this set of evaluation. And yeah, it's kind of surprising because before people were assuming that, you know, for this type of evaluation, definitely text is very important, and doesn't seem to be the case. So we can also scale the data. And here, when we say data, it's more like training iteration. So the number of examples seen by the data set. So what we want to see is just, you know, model keep improving as we increase the amount of training. So we don't see saturation of performance yet, at least on average VQA. And most of the gain actually come from OCR and chart. So by training longer, you can boost the performance on OCR and chart VQA. I think one interesting thing is like if you repeat the same set of experiments, but use ImageNet 1K as your pre-training distribution instead of MetaClip, now you don't see any scaling trend. So here in this plot, you have again the different accuracy for the different VQA tasks. Blue is the model pre-trained on MetaClip. Red is the model pre-trained on ImageNet. And you do see a saturation. And so it's kind of an argument to say we need to move away from ImageNet for SSL pre-training. And maybe one last experiment. So one of the surprising findings during this project is the fact that, okay, by training on MetaClip, training longer, we see a huge improvement on OCR and chart VQA. And so we try to understand a bit better. And one of the hypotheses was that, okay, web scale data contain rich text information and in image. And so SSL can learn, you know, text-related feature just by using this type of data. And so to verify this hypothesis, we kind of design a very simple filter based on VLM, you know, asking, does this image contain any readable text? We get like some subset of MetaClip, which is kind of half the size. And we can, you know, use even more aggressive filter when we get, you know, 1% of the overall MetaClip data. And so look at what the impact in terms of performance in the different VQA tasks when you train on those different subsets. So here's the clip model. Here's like web Dino. So it's like Dino v2 trained on MetaClip data. So on the full data set, this is a Dino model trained on the light filter version. So if this is half of the MetaClip size, and this is like 1% of MetaClip size, right? And you can see that just with kind of adding 1% of data, which are very OCR and chart specific, you see a huge boost on OCR and chart, right? And you see kind of similar performance, you know, maybe a bit of a drop on general, but it's not huge. So, you know, it also means that it's not just throwing more data, but finding the data, you know, that provide the right information to the model. And you just need 1% of the data of MetaClip to be competitive with a clip model, right? Okay, yeah. So yeah, to conclude this second work, so the gap between SSL and clip model, it seems largely come from the data distribution, not so much from the pre-training objective. And basically, even for VQA, you don't need text. That's what this work is kind of arguing. The other thing, which maybe I didn't touch on so much in the experiment, is to show that SSL scale, right? Like since Dino v2, there was kind of this impression that we reach a ceiling in terms of SSL, but actually, if you turn on the right pre-training data, you can make SSL scale and see like a log linear scaling again. And I think one of the conclusion of this work also is, usually when we work on SSL, we spend a lot of time on the model part, the loss, the how to design the algorithm, but clearly data is a key component, and sometimes we have the right tool already, but we are not looking in the right setup. We might not have the right evaluation, we might not have the right pre-training, and so thinking more at the system level setup, I think kind of is one way to kind of push also SSL forward. Yes, so conclusion, but yeah, thank you.